chapter 19, we're dealing with the second law of thermodynamics. And there are different ways of writing it. One, we could write it as delta S of the universe. The increase is for a spontaneous process. But probably the most common way we're going to write it is the delta G of the system is equal to delta H of the system minus T delta S of the system. And so here we don't have to deal with the universe. We just look at it from the system's standpoint. And then we have three different possibilities. If delta G is less than 0, then we say it's spontaneous. If it's spontaneous, that means the entropy of the universe is increasing. And that means the entropy of the system must be increasing, but also the entropy of the surroundings. The entropy of the surroundings, we're going to get a gauge from delta H of the system, because if delta H dumps heat into the surroundings, that will increase the entropy of the surroundings. The other is if it's 0, it's at equilibrium. If it's greater than 0, then it's non-spontaneous. The entropy of the universe must be decreasing in that. The entropy of the universe is decreasing. It could be because of the system, or it could be because of the system entropy, or it could be because of the energy entropy. All right, that's the second law. Now, when we do our calculations, we have restrictions. If we use Appendix D data, is used, then what are the restrictions of Appendix D? And so let's take a look at Appendix D here. Might be hard to read. Try to blow it up. All right, Appendix D says this. Thermodynamic properties of substances are 298.15 Kelvin. We'll just call it 298 Kelvin. Some substances are 1 bar pressure. And so 1 bar pressure is one of the restrictions. For aqueous solutions, solutes are at unit activity, roughly 1 molar. Data for ions in aqueous solution are relative to values of 0. All right, and so basically if Appendix D data is used, then we have a restriction. And that restriction is going to be shown in this way. We're going to add this little superscript here. There's one more restriction, and that is, this superscript refers to standard conditions. And the standard conditions are just stated right there. The pressures are at 1 bar or 1 atmosphere, Depends on what data table you're looking at, because a lot of data is in atmospheres. 1 bar, 1 atmosphere. And if we have an aqueous solution, the concentration is at 1 molar. And so these are standard conditions here for thermodynamic. Now, temperature you would think would be a standard condition, but it's not. Temperature is specified. And the reason for that is not everybody wants to do a chemical reaction at room temperature. Usually you heat it up, and sometimes you'll cool it down. But we do chemical reactions at different temperatures, so it makes no sense to have one fixed temperature. Whereas, we do chemical reactions, at constant pressure, so this is convenient. And then if you're going to pick a concentration, you might as well pick 1 molar. So that would be convenient, so we'll do it there. If you start making the concentration variable, then that really changes the driving force significantly. And so these are the restrictions. And temperature is going to be at 298. This is not, there's no such thing as standard temperature though. No standard temperature in thermo. Now there's a standard temperature for gases called STP, but this is different. This is not STP, this is standard thermodynamic conditions. STP is standard temperature and pressure. And we use standard temperature and pressure when we're dealing with gases. Even standard temperature and pressure is not so convenient because standard temperature for gases is 0 degrees C. You know, how often do we work at 0 degrees C? Don't. And so if Appendix D data is used, then we have restrictions. And these restrictions are here above. And so that means, you know, our calculations are going to be for specific temperature, for specific pressure, for a specific concentration. All right, once we're aware that there are going to be restrictions, what we can do is we can just do some calculations for delta G, you know, and delta G, you know, we know is equal to delta H minus T delta S. I'm going to start getting rid of this system. Because we know it's going to be the system, it's not going to be the surroundings that we're dealing with here in this case. And so instead, I'm going to write the temperature. And so this is going to be delta G naught with appendix D, and the temperature is going to be specified down here as a little subscript. And so this will be at standard thermodynamic conditions at 298 Kelvin. And so we can determine that using the equation over there. You know, that equation over there is for any condition. This equation here is just for the specific condition. So this is going to be delta H naught at 298 Kelvin plus T delta S naught at 298 Kelvin. So over here, we could have this at any concentration, any pressure, and any temperature. And so this is flexible. But you know, the problem is we have to calculate these values at those particular temperatures and pressures. Over here, well, we can calculate these values. You know, delta H naught is just using the data from appendix D. It's just the delta H of formations right here of the products minus the delta H of formation of the reactants. Delta S naught, we calculate using this absolute entropies over here. So it's the sum of the absolute entropies of the products minus the sum of the absolute entropies of the reactants. So this is one way of calculating delta G naught. It turns out that there's another way of calculating it too, and that's by using Hess's law. You know, delta G is a state function, so Hess's law should work. What Hess's law says is this column here. And so we use this first column and the third column. The fourth column we're never going to use. This column here, actually I shouldn't say never because we might calculate, you know, amount times C times delta T for different substances. Get the heat. But this column we haven't used yet, and these are delta G naughts of formation. And so what is formation? Do you remember the little f, what that stands for? That stands for formation of 1 mole of substance from the elements in their standard state. And so if I look at delta H of formation of aluminum solid, we're forming 1 mole of aluminum solid from aluminum solid. So we're going from aluminum solid to aluminum solid. Temperature is at 298, so we start at 290, we end at 298. Obviously, we're at the same thing. And so the delta H of formation is going to be 0. Well, the same thing with delta G of formation, it's going to be 0, but we have other substances where it's not 0. And so using Hess's law, we can come up with this equation. And that is, it's the sum of the delta G's of formation of the products. And since energies and delta G's are extensive, that is, they depend on the amount, we have this factor, mu P, which is the moles, times delta G of formation of the products, minus the sum of mu R, delta G of formation of the reactants. And so this gives us 2 ways we can calculate delta G under this restriction here. All right, so let's go ahead and do a calculation right now. We'll do something very simple here. we're going to look at this H2O liquid going to H2O gas. And we're just looking at the vaporization of water. And so what we'll do first is we're going to calculate delta G naught. And this is going to be at 290 Kelvin. So this is equal to delta H naught at 298 Kelvin minus T delta S naught at 298 Kelvin. Temperature is going to be at 290 Kelvin. And the same thing over here. You know, this temperature is 290 Kelvin. That's where we're restricted to. And so let's first figure out what the delta H is for this. Well, the easiest way is just to sum up the delta H of formation of the products minus the sum of the delta H of formation of the reactants. And so here, delta H of formation of the product would be the formation of H2O gas. Let's take a look at that. And so delta H of formation of H2O gas is minus 241.8 kilojoules per mole. How many moles do we have? We have 1 mole. And so it's just going to be minus 241.8 kilojoules. Moles cancel. Delta H of formation of the reactants is H2O liquid. H2O liquid is minus 285. So this is minus 241.8 minus a minus 285.8. It would be plus. And that gives us plus 44.0 kilojoules. So our first term here is 44.0 kilojoules. Okay, minus T, which is 290 Kelvin, times delta S naught. And so H2O gas to H2O liquid, well, we just look at the standard entropy. Not standard, sorry, the absolute entropies. And so H2O gas has an absolute entropy of 188.8 joules per mole Kelvin. We have 1 mole, so it's just going to be 188.8 joules per Kelvin. And then we have 1 mole of H2O liquid, which has an absolute entropy of 69.91 joules per mole Kelvin. Again, 1 mole. And so let's calculate that. Can somebody calculate the? We did it earlier. But, somebody calculate the entropy change here. What did you get? So I'm just taking 188.8, that's the entropy of the products, minus the entropy of the reactants, 69.91, 118.89. This is going to be 118.89. The units are going to be joules per Kelvin. So the units don't match here. The Kelvin cancels, but we got kilojoules minus joules. And so we're going to have to convert it. So let's go ahead and divide by 1,000 joules per kilojoule. And then we got it. And so I'll take 118.89 times 298 divided by 1,000. That's 35.42. And so I have 44.0 kilojoules minus 35.42 kilojoules. Okay, what is this telling us? This is telling us that the energy is increasing. Do you want to increase energy or do we want to decrease energy in chemical reactions? We want to decrease energy. And so this is not good. This is bad for driving force. You know, if we want to drive this reaction forward, then this is stopping it. But if you look at the entropy, you know, is the entropy going up or is the entropy going down? The entropy is going up. We're going from liquid to gas. So we can see it here. It's going up. So the entropy is positive, but we have this negative sign here, so it's going to make it negative. And so this is good. And so from this version of the second law, we can see how energy and entropy terms balance. You know, if we get them in the same units, here's the energy term, here's the entropy term. And which one wins in this particular case? Well, which one wins is the bigger term. And the bigger term meaning, in this case, 44 versus 35.4. So we have 44 bad, 35.4 good. It's not enough good. And so when we add these up, it's going to come out to, is it 35.42? I'll just 8.57. Okay. It comes out to plus 8.57 kilojoules, which means that it's greater than 0, so this is non-spontaneous. And so the entropy wasn't enough. Even though the entropy was good for driving force, it wasn't enough to overcome the bad. And so it's non-spontaneous. We're going to come back to this in a minute. But there's another way of calculating delta G, which might actually be easier. The other way is by using the delta G's of formation here, like you did for delta H's. And so let's take a look at the alternate method. Alternatively, we could have used Hess's law and delta G's of formation. So again, this has to be restricted to standard thermodynamic conditions and 298 Kelvin. And so this is going to equal the sum of the delta G's of formation of the products minus the sum of the delta G's of formation of the reactants. So we need to know how many moles, because the more moles you form, the more energy it's going to take, or the more energy it's going to release. And so we go to the product. The product of H2O gas, delta G of formation is minus 228.6. And so what we have here is we have 1 mole of H2O gas, and it's 228.6 kilojoules per mole. So moles cancel, it just gives us kilojoules here. Minus, well, we only have one reactant, it's H2O liquid, and its delta G of formation is 237.1, negative. So this is, this is negative 228.6. And so this is minus 1 mole of H2O gas, actually H2O liquid, sorry, that was gas, times, what is this, 237.1 kilojoules per mole